This is the Antimatter factory here at CERN. It's where we produce, store, and study antimatter in order to learn more about its properties. My name is Dr. Clara Nellist, or Particle Clara, and I'm usually on the ATLAS experiment on the Large Hadron Collider here at CERN. But today I was at the Antimatter factory for a live with TikTok UK as part of their summer skills program. So this week has been STEM week, so science, technology, engineering and maths, and we finished the week off with a live at the Antimatter factory. And I was joined by Professor Jeffrey Hangst, who is the spokesperson of the Alpha G experiment here in the Antimatter factory, and we did a live tour of the facility. Excellent, welcome.
Hi everybody.
So your camera, yeah, perfect, your microphone. So any noise that you hear is fine. If we don't look worried, you shouldn't be worried. So we're here at the Antimatter factory at CERN. So this is part of TikTok UK's Summer Skills program and it's STEM week. So we're here at CERN and we're in the Antimatter factory. So I have Professor Jeffrey Hangst who's joining me here in the Antimatter factory because this is where he works. So antimatter has been around it's been around since the beginning of the universe. But we've known about it for about 100 years?
Yeah, since the late 1920s was a theoretical prediction about antimatter by Paul Dirac, the famous theoretical physicist from the UK.
Yeah.
Experimentally, we've known it since 1931, and now it's my day job.
Excellent. So can you tell me why is antimatter so important?
Well, antimatter is interesting because of its absence. Because the Big Bang, we think, was some huge explosion of energy that created everything that we have. When we do things like that in the laboratory, we always get equal amounts of matter and antimatter. That seems to be a physical law. So we have no idea what happened to the antimatter that should have been with us from the Big Bang. Matter and antimatter can't coexist, right? They annihilate, release a bunch of energy. That's what makes it so interesting from the science fiction. I'm sure we'll get to that a little bit later. But so we're trying to understand the properties of antimatter to see if maybe it's not really identical, but somewhat different than the matter, and nature somehow preferred matter.
Yeah, and so antimatter, it gets created in many different ways around the world. So this isn't the only place in the world to make antimatter, but it's special because here you can create a lot of it, and also you can hold it, right?
Yeah,
and that's the really special bit.
That's really the key to what goes on in this laboratory. There are several different experiments here, but we're all interested primarily in holding on to antimatter so that we can study it. In particular, this machine, the anti-proton decelerator, is about making antiprotons, the equivalent to the hydrogen nucleus, right? Element number 1. So this machine makes and slows antiprotons, and then we manipulate them, slow them down, stop them, and do experiments on them to characterize their physical properties.
Excellent. So I see we've had a lot more people join us in the last few minutes, and you're joining this live because it is part of TikTok UK's Summer Skills program. So TikTok UK wants you to learn things over the summer, and this week is STEM week. So we're learning all about science, technology, engineering and maths, and today we're going to be talking both about antimatter here at CERN, but also what are the skills that you need to be a scientist. So maybe we can go on to that.
Okay.
So I'm a scientist because I read a lot of science fiction, and also I'm very curious about the world. And a lot of people think that you have to be like perfect grades to be a scientist. And I think studying helps, it's important, of course. But for me, curiosity and like a stubbornness are really the important skills that you need
Some
to be.
would say a very high threshold for boredom, not just stubbornness. But I think also creativity is a very important part that most people don't realize. Studying science in high school or wherever you are is sometimes a little bit cut and dried. Mm-hmm. The actual business of science is a much more creative endeavor. And I think that's what actually separates great scientists from average scientists is the creativity part. There's no recipe for doing what we do. You may get the wrong impression by reading a physics textbook. The actual business of science is not scripted. Making it up as we go along, and creativity is very important.
Yeah, I would also say that I think people think that scientists, and so we've worked very hard to get where we
Sure.
are, but people think that we're super smart. And actually, I feel stupid most of the time because we're wrong a lot, but in a way that we're learning consistently. So you have an idea, you're testing it with your experiments, and sometimes you're wrong, and that's okay as long as you learn from being wrong.
Sure.
And then you update the information that you have, and then you use that to get to move into new ideas, to make new experiments, and eventually collectively we're then right.
Sure. It's not a straight path. It's a lot of false steps, a lot of missteps, a lot of bad assumptions that you have to learn from. What's cool here though is that pretty much everything we do here at CERN, we're the first people to ever see that.
Mm-hmm.
You discover something that's no one, maybe in the whole universe, has ever seen before, because we're pushing the frontier. That's what really inspires me, that to be the first person to know something fundamental about the universe, I think that's really cool.
Yeah, it's definitely an amazing thing about working here is that you will look at a new bit of information, something we've just learned, and absolutely nobody else in the world has seen that before.
In fact, that's the whole point. You got to be first. Nobody remembers who came in second place in this business.
Excellent. So you can ask us questions during the live. So I saw that one got pinned and we missed it. I'm sorry about that. But if you ask your questions, then we're going to try and answer as many of them as possible. So if you want to know what it's like to be a scientist, if you have questions about the antimatter factory here at CERN or anything you want to know, then do let us know and we will answer as many questions as possible. So somebody's asking, what is the antimatter factory? Is it some sort of detector that we're building?
That's a common misconception that every experiment at CERN is some huge detector. This is not that at all. It's actually based on taking particles of antimatter and slowing them down. Normally we're in the business of accelerating particles at CERN to the highest possible energy. But here we create antiprotons. That sounds very exotic, but really you just run a high energy beam of protons into a piece of metal. And then they're collected in what we call a storage ring. We're standing on top of it now. It goes around the inside of this building a few hundred meters in circumference. So we're catching antiprotons and then slowing them down so that we can then distribute them to experiments who will stop them, actually hold on to them, and then do experiments on them. So that's the essence of the antimatter factory. And in case you're wondering, it really is a factory. It runs 24 hours a day. There are 3 shifts a day in the experiment. We run from 7 to 3, from 3 to 11 at night, 11 to 7 the next day, just like a real factory where I grew up, which was in Western Pennsylvania in the United States, the steel capital of the United States. So I spent my life trying to avoid working in the factory, but here I am.
So somebody's asking, are not protons made of energy? So with Einstein's equation, E equals mc squared, we can change energy and matter into each other with the sort of conversion factor, the speed of light squared. That's what that C is. And the speed of light is a massive number. So you can take a little bit of matter and turn it into energy, and then that energy can be turned back into matter as well. So it is protons, photons, all of the particles, they are energy, but they're energy in a specific form. So excellent. We've got lots of great questions. Yeah, and I'm from Coventry in the United Kingdom. So hopefully we've got a lot of UK people joining us with TikTok UK today. And yeah, if you want to be a scientist one day yourself, that's what we're talking about today during the live. So you said your experiment is behind us?
Yes.
So what's going on behind us?
So we're interested in a very particular type of antimatter, the anti-hydrogen atom. Okay, so hydrogen is the simplest atom, just one proton, one electron. You've all seen the cartoon diagram of what an atom looks like. The only antimatter atom that we can make is anti-hydrogen. One antiproton, one anti-electron, which is also called a positron. This is the only place in the world where that's ever been synthesized. My experiment is the business of making and holding anti-hydrogen and then studying its properties to compare them to hydrogen. Our theories say that they should be identical, and that's what we're trying to test to see if that's actually true, if atoms of matter and antimatter are actually identical.
Perfect. And so what did you find? Because you had a massive result come out a little over a year ago, right? And this was a very exciting measurement.
We have lots of exciting measurements in the past. The most recent one, which was really fancy, was what happens if I have some antimatter and I drop it in the gravitational field of the Earth? There have been lots of speculation about how antimatter should behave in the Earth's gravitational field. But in 2023, actually, we did the first experiment where we took some antihydrogen and dropped it to see if it would fall up. There are actually a few theories that said it would go up instead of down. Turns out it falls down, as most people expected. But that was an incredibly difficult experiment. It took more than 30 years of development to get to the point where you could make an antimatter atom and release it. So we're very proud of that.
And it was a very celebrated result here at CERN. So we have another question on the screen. What exactly is antimatter? Oh, so we should go back and explain what antimatter is.
We started a little bit with this, maybe you tuned in later. So you and I are made of particles, right? You've all had the periodic table in chemistry class. Those elements are made of three things: protons, neutrons, and electrons. Three basic particles make up everything that we see. We learned back in the 1920s that there's another possibility, that an equivalent but opposite particle for each type of particle that we know about can be produced. These are the antimatter particles. So they have opposite charge and the same mass as their matter equivalent. By the way, that's an experimental question. That's what the theory says, but this is something that we're actively testing in this building, the equivalence and direct oppositeness of matter and antimatter.
Because that's, just to interrupt quickly, that's also another skill and important feature of being a scientist, is you don't take any, I mean, we have facts and we stand on the shoulders of giants and we don't destroy the knowledge that has come before, but just because we think something should happen, we have to test whether it actually does happen that way, because it could be that we're wrong.
That's right, and we love to be wrong. We love to learn something new that contradicts what we thought we knew. That separates us from many other endeavors. We're really hoping that what we know now is wrong at some level. So we put it to the test all the time, and that's, you must be willing to challenge those assumptions if you want to be an active scientist.
But so what we know right now is that antimatter is almost identical to regular matter, so these protons, neutrons, electrons, and the other particles that we know, but it has this opposite electrical charge. But otherwise it's behaving very
well. That's what we're testing. That's the whole purpose of this existence of this building. The other interesting characteristic about matter and antimatter is that they can't coexist. If they meet each other, all that rest energy that Clara was talking about, this E from the mc squared, annihilates and produces new stuff. On a microscopic scale, that's kind of the most violent thing that we know about that happens naturally. Matter and antimatter, when they meet, that's a very energetic outcome. And that's what makes it so interesting in science fiction. We can talk more about that later, perhaps.
Excellent. So your experiment's happening behind us?
Right. About 2 levels down from us, we're actually stopping antiprotons, mixing them with positrons to make anti-hydrogen atoms, and then trapping them so that we can study them. We study them with lasers to see what their structure is, or we drop them. Right now we're in the business of turning on the experiment that drops them.
Nice.
It's called alpha G for gravity. So we've already had a few months this year with the other experiment to study their internal structure. Now it's all about gravity.
Excellent, because hydrogen is one of the things in our, I mean, it's one of the most abundant things in our universe, but it's also one of the things we know the best.
That's right.
So then being able to compare it to anti-hydrogen is a good experiment.
Should we be a bit technical?
Yeah,
quantitative?
technical, yeah.
Okay. So hydrogen was how we learned about quantum mechanics. It's the first atom that was ever quantized. I have to bring this up because I'm a professor in Denmark, and the guy who did that was Niels Bohr, the very famous Danish physicist. He's the one who told us that energy levels in atoms are quantized, okay? Now, we can measure those energy differences. It's essentially the color of hydrogen by shining a laser on it to see what kind of light it likes to absorb and emit, right? Now we can make very, very precise measurements of the frequency or the color of the laser light that anti-hydrogen or hydrogen likes. So my experiment is about comparing those colors of hydrogen and anti-hydrogen to 15 decimal places, right? So very, very precise and accurate measurements which are characteristic of atomic physics rather than the high energy physics that we normally do here. So that's the business of alpha. Make some anti-hydrogen, measure it, compare it to the very, very well-known physics of hydrogen.
So there's a question here, oh, it's gone, but I saw it, and it was asking about whether, I didn't fully read everything, but it was about energy and DNA and whether atoms have DNA. And I think it's a good analogy that the hydrogen, for example, has this quantized structure. So it's not like DNA in the way that makes up people and animals, but it's a very unique signature for the atom that we can then look at and compare to the anti-hydrogen.
One of the reasons we love hydrogen is that it's so simple. DNA is incredibly complicated. I wouldn't touch that stuff. But hydrogen is the simplest atom. That's why it's so elegant. We think we understand all the physics of hydrogen. So anti-hydrogen is an extremely elegant comparison to make.
I see another question. Does antimatter hydrogen occur naturally in nature? If yes, what kind of events create it?
Okay. As far as we know, there's no anti-hydrogen in nature. It would immediately meet some other matter and annihilate. In fact, that's one of the puzzles of the universe, is what happened to all the antimatter that should have been created at the Big Bang? Why didn't that just annihilate the matter that we have? So no, you have to create anti-hydrogen in the laboratory. You can't observe it from a cosmic ray or some other energetic event. We've never seen it anywhere but right here, actually.
Yeah, so this is really one of the big mysteries in the universe, is where did all that antimatter go? What is that slight difference between matter and antimatter?
If there is one.
If there is one.
Could be our theory just wrong.
Yeah, which is more exciting.
Yeah,
as we were
exactly,
saying.
absolutely.
We actually, scientists love to be wrong, because then you've got to rewrite the theories, you've got to go back to the drawing board, and that's exciting as a scientist. So if you want to be a scientist, you don't have to be right all the time. You just have to update your information as you do new experiments. Excellent. So, oh no, I thought there was another question, but it's gone. So do let us know if you have more questions. Maybe we could move slightly to see a different background.
You want to see more of the experiment?
Yeah, let's go see more of the
here.
experiment. So we're going to take you with us.
So right behind us now is the top of the alpha G experiment. That's the one that's going to hold on to some anti-hydrogen and then drop it to see how it accelerates in the gravitational field of the Earth. We've already proven that it falls down, and it falls down in a similar way, but we need to measure that acceleration very precisely. We want to know that it's really exactly the same. And that's what my crew is setting up to do right now. By the way, teamwork is extremely important if you want to be a scientist on this kind of an experiment. Clara works on a really large experiment with thousands of physicists. Alpha is a little bit more compact. We have about 60 physicists, but none of this is something you could do in your own lab at your university, right? CERN, it serves that purpose of bringing many groups together in a cooperative manner. That's a very important aspect of working at this type of experiment.
Yeah, it's also one of my favorite things about working here at CERN is that we have people from over 100 different countries. So if you're watching and you think, yeah, but my country doesn't do this kind of science, you can still be involved. I mean, I'm British and I work at a Dutch university. You're from...
I'm an American. I work at a Danish university. I live in Switzerland. Typical physics.
Yeah, so we move around a lot, and you don't need to be from a specific nationality to work at a university, and then a lot of universities send people to work at CERN. So we have some positions where you can apply to CERN directly and get a job through CERN, or you can go and work for a university and then get sent here. And we have, I think, around 20,000 people associated. Yeah, so it's a really collaborative. It's international. There's people from lots of different backgrounds. You were explaining about where you're from and the factories nearby. I'm also from I think a similar background.
Are you?
Yeah.
Okay.
So you don't have to
No.
be from a particular background to be able to work at CERN. We have lots of different people here.
But you do have to work really hard.
Yeah.
There's no question that most people who are in physics, they don't consider this a job. This is their life. This is a calling that we're happy to do. I've had guys tell me that they would do physics for free if they could. So this isn't your typical job. This isn't a 9-to-5 job. This is evenings and weekends and lots of time put in, especially if you're a experimental physicist working in a lab.
Yeah, and it's also it's a privilege to work
Absolutely.
here. It's
If you may have missed it in the beginning, everything that's done here is pretty much unique in the world. There's no other facility where you can do what we're doing.
yeah, great. So we were looking at your experiment
Do you want to
behind
look?
us.
Let's watch what these guys are doing. So if you want to hold on to antimatter, you need some really strong magnets. And if you want really strong magnets, we often use the phenomenon of superconductivity. That means when certain conductors are cooled off to really low temperature, they lose their resistance to electricity. So in order to cool the magnets down, we use liquid helium. And what these guys behind me are doing now is they've got a dewar with 500 liters of liquid helium, and they're about to transfer it into the alpha G experiment, right? Again, CERN, the LHC, the big accelerator here, is also cooled down to just a few degrees above absolute zero.
Which is colder than outer space.
That's right.
Yeah.
The other thing that you need for antimatter is vacuum. You need to remove all the matter from your machine so that the antimatter doesn't collide and annihilate. So we also have the best possible laboratory vacuum, which is comparable to interstellar space. So a very exotic environment here if you want to hold on to some antimatter.
Yeah, but I mean, we're both experimental physicists, and so we really like hands-on work.
Sure.
And the experiments here, you also, you have to get stuck in. You have to, build them. You can see a lot of cables in our experiments around here. That's one of my favorite things as well about being an experimental physicist. I'm a hands-on person.
Yeah. We build everything here, right? I mean, you can't buy an antimatter machine. As Claire points out, it's cabling, a lot of plumbing. You'd be surprised the practical skills that you would learn in experimental physics. I always tell people that if you're a true experimental physicist, you can fix anything.
Yeah. So, in fact, I was cabling up the lights in my ceiling earlier.
Of course you would, yeah.
That's
Why
what
would you pay someone to do that? Right?
Exactly. That's what my PhD taught me, was to be hands-on and do my own cabling. So we do have theorists here at CERN. That is a different field of physics, a different type of physics. But mostly we're focusing on experimental physics here today. And also that means we have a lot of technicians, engineers. It's not just physicists that work here. There are a lot of different ways to work at CERN. So if it's something that you're interested in, then do have a look at all of the different options, because some people think of science as theoretical physics, and people who really do a lot of the mathematical calculations and sit in front of their computers. And we do a lot of simulations and programming, but there's also a real hands-on component to it. Great, so I'm going to see if we have, so can you tell us a little bit more about the detectors? So you've dropped your antimatter.
Yeah.
How do you know where it's gone?
Yeah, so we trap it in kind of a magnetic bottle that's vertical. We sort of let it slip out the top and the bottom. So because of gravity, slightly more goes out the bottom than the top, because these atoms are bouncing around inside the trap. You know these lottery ball machines where the balls are jumping around, and if you take off the thing, one will come out? It's kind of like that. These are jumping around. We open the doors a little bit at the top and the bottom. Some will go down, some will go up. But because of gravity, slightly more will go down. Okay? Now, when they come out of the trap, then they're not confined anymore and they're going to hit some matter and annihilate. So we just count how many go up and how many go down. We're really, really good at detecting that annihilation. That's a microscopically violent event. CERN is all about detecting those type of events. In fact, Clara's experiment is infinitely more sophisticated at doing that than what you need for the antimatter.
And it's a flash of light you get?
Actually, it's particles.
Particles,
So, okay, when you go on popular science or science fiction, you'll hear people say matter and antimatter annihilates and they make pure energy. That's only true in one actual event, and that's when electrons and positrons annihilate. They make light, high energy light. Everything else makes new matter and antimatter and energy. So when an antiproton annihilates, it's got a lot of mass to annihilate. It creates subatomic particles that come screaming out of the experiment close to the speed of light, and they're very easy to detect. So we can see them with our detector that surrounds the whole vertical machine. We just count. 70 went down, 30 went up, right? And you have an experiment.
So we have another question. Oh, so what type of detector is used for detecting this antimatter? So you say the particles are coming out?
Yeah, particles are coming out, and the ones that are in particular, if we want to get a bit technical, they're called charged pions. Those are subatomic particles that are unstable. You have to make them in the lab, but they're the main decay product when an antiproton annihilates with some matter. The charged ones come screaming out. We have two ways in our system here of detecting them. One of them is actually kind of a fancy CCD camera. It's a segmented piece of silicon, like the chip inside your cell phone camera, and it reacts when a charged particle goes through it, okay? In physics lingo, these things are called pixel detectors. Ours is a silicon vertex detector, but it's a very similar thing. It just, the particle passes physically through a piece of silicon, leaves some charge, and you count it, right? And you do it in a position-sensitive way because it's a segmented detector like the chip in your camera.
So we have another question, which is how is antimatter made? This might be a good point now that we're at the halfway point to wander over to the
Okay, you want to go to ELENA?
Yeah.
There are other experiments here.
Yeah.
Alpha is not the only one. This is called Asakusa. It's another experiment.
See it here.
Base is over there.
Where's base?
Base is
Over that way.
over there and down.
Yeah.
They're interested in just antiprotons, not anti-hydrogen.
So there's multiple experiments here and they're all looking at slightly different properties of antimatter. But as we said, this is the antimatter factory, so this is where all of the best antimatter is. So there are other ways to make antimatter. Your bananas and your avocados make a little bit of antimatter. I think if you've eaten a banana today, you have about 3 positrons a day or something like this. I don't know the exact number, but it's something like that. So you have a couple of antimatter particles that get formed inside of you, but it's harmless. They go away because even though it is microscopically a lot of energy when they annihilate inside of you, it's not very much at all. So you have, if you've eaten a banana today, you might have some antimatter inside of you, but it only lasted for the smallest of moments and then it's gone.
So the proton synchrotron is the oldest accelerator at CERN. It dates back to the 1960s. You run protons into a target, a lot of stuff gets produced. This is E being converted to M in Einstein's equation. Energy from the protons being converted to mass. Some of that mass are particles of antiprotons, and they come and are injected into this ring, so-called storage ring, because it's at a constant energy when they come in. They stay there but are then decelerated and then transferred into another ring, which is called ELENA. We're going to look at that in a minute. Further decelerated and then sent to various experiments. By the way, this process takes 2 minutes. We get a bunch of protons, make antiprotons, slow them down, kick them out every 2 minutes to the users, the experiments. So there's my experiment alpha. You see there are several others. Every 2 minutes, this facility can send antiprotons to 4 different experiments each time, okay? So the beam gets split up in 4, boom, 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 boom. We catch it when they send it to us, okay?
So we have 2 questions. So the
Okay.
first question was, does antimatter have mass?
Yes.
And the second one was, how much antimatter is made?
Okay, so we just talked about every 2 minutes we get this shot of antimatter. And how many particles are there? Well, the order of magnitude is 10 million
10 million.
every second minute. Okay? Now, does that sound like a lot? You remember from your high school chemistry, a gram of hydrogen, you remember Avogadro's number? Is it 6 and 23 zeros? Right, that's 1 gram of an atom like hydrogen, right? So a million or 10 million is really nothing. It's vanishingly small. It's still a lot more than things like Higgs bosons that Clara makes, but it's a microscopic amount of antimatter.
So it's a lot for studying? Is that a lot for studying?
It's plenty for studying because essentially we deal with every single atom. We know the fate of every single antiproton that we deal with because we can detect them so readily. So it didn't seem like that when we first started out, but right now we have plenty of antimatter for doing fundamental physics.
Excellent. So somebody's asking if this is ELENA. Yes, this is the ELENA decelerator that we can see here. So a decelerator works exactly the same as an accelerator, just
except when you decelerate a beam, it gets bigger. And if you don't do something to counteract that, it'll just hit the wall. Conversely, when you accelerate a beam, it gets smaller for free. This guy, Simon van der Meer, won the Nobel Prize for figuring out how to deal with antiproton beams back in the 80s. Okay, so it's much, much more difficult to decelerate than it is to accelerate.
So I'm learning new things as well. So the decelerator that we see down here, it does have a lot of the features that we would see in a regular accelerator though.
And more.
And more.
Yeah. The blue are the dipole magnets. You can see they make a bend.
Yeah.
The beam goes through an angle. So that's to get them to go around in a closed loop, right? There's 6 of those in ELENA. The orange magnets are for focusing the beam. They kind of act like lenses do with light. So they're for maintaining the beam size inside the accelerator. Those physical principles are exactly the same in the LHC. This is kind of cool for visitors because you can see a complete accelerator in front of you, a decelerator in this case. But all the physical principles scale all the way to LHC energies.
And we also have, so you were talking about the cooling.
The blue thing
yeah.
is called electron cooler. That's different than what van der Meer invented, but that's what is the dominant cooling in ELENA. And what you're doing there is overlapping a beam of electrons with the circulating antiprotons. And the electrons are more well-defined. They cool the antiprotons through collisions.
Great, so as you were saying, because this is a decelerator, then the anti-protons get further away from each other and we want them to both be at the same...
We want to have the same energy. Anything that's produced in a target through collision has some randomness, right? They're not all the same energy, they're not all the same angle. All of this facility is about controlling that and all the way down to very low energy.
So we have another question, which is, it's still particle physics themed, but is it even theoretically possible to knock a single proton out of an atom without huge energy? And I would say it depends what you mean by huge energy. So we actually have a big result that came out with the Large Hadron Collider recently. I'm just going to turn around so you can see while we talk about this. And that was the fact that as well as accelerating protons with the Large Hadron Collider, we also accelerate heavy ions. So this is another completely different form of research that we do where we want to study the very early universe. So that doesn't happen here in the Antimatter factory, but that's with the Large Hadron Collider. And with heavy ions, sometimes they can get very close to each other and they don't actually collide when these beams of heavy ions like lead ion get very close to each other. And the electromagnetic field between the two of them can knock protons and neutrons out. And this isn't the same as like a nuclear reaction. You've probably heard a lot or read a lot about those. It takes energy to do this, but it's not a lot of energy, I would say.
No, well, in fact, the simplest way to get a proton is to break a hydrogen atom apart. And that's the very first thing that starts the acceleration process at CERN. We got to get protons. They come from a gas bottle of hydrogen. First break up the molecule, then break up the atom. That's a very low energy process compared to anything else that happens here.
So we can turn around because we got a nice diagram up there. So you can see this nice diagram showing that we have the protons coming from one of the pre-accelerators. I'm trying to see where my finger goes, there it is. One of the pre-accelerators to the Large Hadron Collider. So the Large Hadron Collider is just one of many accelerators we have in a chain. It's the final one with the highest energy. And then the protons that come from the proton synchrotron hit a target, and then that's how, from that interaction, that's how the antiprotons are created in the collision, and then they start their journey into the antimatter decelerator, and then eventually into the ELENA.
ELENA is new, by the way. We got it in 2021, where we first started to use it. We've had the AD since the year 2000.
Great. So there's a question, does either matter or antimatter defeat the other? But it's really an equal process.
No, it's, yeah, they annihilate each other. Nobody wins. It's a complete instantaneous conversion of their mass energy into energy, which then converts mostly back into mass again. So yeah, they both are completely lost and you create new things.
Great. So I saw another question that passed by briefly. Oh, I've zoomed us out here. This is very good. Somebody asked if we're closer to Switzerland or France right now, and we're right on the border.
We're in France right now.
But
we're actually in international territory is the proper answer. But we're on the French side of where the boundary runs.
But the border is within our sight.
The border is within, yeah. If I leave to go out of CERN from here, I will cross into Switzerland.
Yeah, and so the protons on their journey cross the border multiple times.
Yeah, these machines are both in France, but the LHC and the SPS cross the border.
Yeah, excellent. So I'm going to see if we have another question. So just to let you all know, we have about, so not just yet, we have about 15 minutes of this live left. So if you happen to have just joined us, then this is for TikTok UK's Summer Skills program. And we are here at the Antimatter factory at CERN as part of STEM Week. And so my name is Dr. Clara Nellis, Particle Clara on TikTok. And I make videos here at CERN about our research, and I love to tell you about what we're doing here at CERN. And I'm joined by Professor...
I'm Professor Jeffrey Hangst. I'm from Aarhus University in Denmark, but I'm the spokesperson of one of the experiments here that deals with antimatter.
Yeah, so we didn't actually cover that bit. So you're the spokesperson.
Yes.
You're the boss of your experiment.
I originated it, yes.
Yeah.
And this current experiment started in 2005. So we're 20 years now. This is my third anti-hydrogen experiment, all at CERN. But yeah, this one is the most successful and started in 2005.
Excellent. So we're talking about skills. This is the Summer Skills program. What skills do you need to lead an experiment? Is that different from being a scientist?
I think so. First, you need to really have command of the science. This isn't a management job that you could bring in a consultant to do. You really have to know everything about the experiment. And I think the most important thing is to be open to listen, to listen to new ideas. Some people try to lead by forcing their way, and there's no one singular path from what we don't know to what we will know. So I think it's very important to respect and to listen to everybody and their ideas, because people who go into science, they don't want to have a boss, right? They're independent. They're very ambitious and creative. You don't want to stifle them. So I think it's the most important thing is to not be afraid to collaborate and to listen. Even the graduate students, undergraduates, they have great ideas, and you need to be open to that. You have to have a lot of patience. We call it herding cats. It can be very much like that, because there's some really strong personality types in a collaboration like this.
Great. Something else I did want to touch on, because you've had some fun visitors to your experiment,
yes.
as well as the visitors we have right now. But science is cool, right?
Yes, science is cooler than I ever imagined, because we have a VIP visitor program, and some of the people who come through are rock stars. And I'll just be in my lab and I'll get a call and say, hey, can you give a tour? And I say, yeah, who is it? Well, it's Roger Waters from Pink Floyd. Yeah, I think I can manage that. So we've had a lot of these through, and I've become friends with quite a few of them. Roger is an example, someone I can send an email to and he'll answer. I've met him multiple occasions. So they're just like you. They're people and they're fascinated. They want to know what's going on here. And it's always a lot of fun. I'm an amateur musician also. I play in a rock cover band. So I feel I can communicate with them pretty well. But it's been an amazing opportunity to meet some of these guys coming through.
There's often actually an overlap. I mean, as someone who is very not musical, I love listening to music, but I never learned the skills, which also, as a teenager, I thought you were either good at music or you weren't. You were either good at painting or you aren't. And what I've finally learned through
practice.
Well, yeah, it's all about practice.
Yeah.
And it's the same with being a scientist. A lot of people think, like, I'm either good at maths or I'm not good at maths. And it's not true. It's all just practice.
Although there definitely are people who are born with an advantage in music and in science. I think that's true. There aren't many people like that who really distinguish themselves by natural ability, but they do exist. But hard work is really the key to either of these things.
But you don't need to be a Mozart or a Curie or an Einstein, or
No.
You don't have to be a genius to be good at something, and to get the fulfillment and the enjoyment of doing a career in science, for example.
Persistent. You need to be persistent.
Yeah.
You need to never give up.
That is one of the themes. Right, I'm going to check to see if we have any more questions. Maybe we can show, I'm going to bring this a bit closer and show people the experiment again. Oh, so there's another question. What's the difference between the opposite charge of an anti-electron and the positive charge of a proton?
So the anti-electron, the positron, and the proton, in theory, have the same magnitude of positive charge. Okay, but again, that's something we're measuring here. The base experiment right beside me is measuring very precisely whether the antiproton and the proton have exactly the opposite charge in the magnitude. Theory says that charge is quantized exactly, that the positron and the proton both have 1 unit of elementary charge. But again, if you don't remember anything else I told you today, that's an experimental question. It's subject to test, and that's what we love to do.
So I saw another question, because we kind of touched on, actually there were 2 questions. So one question is there an anti-Higgs boson? Which is a great question.
Excellent question.
So the Higgs boson doesn't have electrical charge, but it could be, according to some of our theories, that there could be other, so maybe not anti-Higgs bosons, but there could be other types of Higgs bosons. And this is something with the Large Hadron Collider we're investigating, but because it doesn't have an electrical charge.
But in general, we consider the bosons to be their own antiparticle, right? So the photon is the other, is the example that the carriers of the fundamental forces, bosons, are their own antiparticles. That's so. But again, there's a lot of exotic theory, and what we love to do is find the next thing. So I'd say the jury is out.
Yeah.
we've had the Higgs boson for what, 13 years now. We're just learning about it.
Does antimatter meeting matter produce more energy than it takes to make the antimatter?
Excellent question, because that's where all the science fiction is, right? If you had some antimatter, that would be the ultimate rocket fuel, right? You could launch a space shuttle if you had 1 gram of anti-hydrogen, right? 1 gram would launch a space shuttle. The problem is that you'll never have that. 2 reasons. It takes much, much, much more energy to make it than you would ever get back, the way that we do it, right? It's a really losing proposition. The other thing is it would take longer than the age of the universe to make a gram of antimatter in the way that we do it, the way that we know how to do it. And that's not just a technical issue. That has to do with the actual fundamental strengths of the forces in nature. So there's not a knob you can turn or a bigger machine you can build to make more antimatter. So the answer is it's a complete losing proposition for everything but fundamental studies of how the universe is screwed together. Now, just so I don't sound like an idiot in 200 years, the more precise answer is there's no direct line between here and there in the physics that we understand today. So some revolutionary concept would have to arise for us to get our hands on any kind of macroscopic amount of antimatter. If you found some, say some interstellar object comes flying by, happens to be made of antimatter, that's a truly amazing source of energy, but we don't think that's how the universe is put together. And if you did see that, you should run the other way.
Yeah,
Don't approach that.
If you see antimatter aliens, don't high-five them.
No.
So the other thing we touched upon, but maybe we can mention again now, is the storage of the antimatter.
Yeah.
How do you store it in your facility?
So if it has a charge, like the antiprotons or the positrons, that's relatively easy. You can use electric and magnetic fields that work on charges to make what we call traps, particle traps. So a combination of electric and magnetic field, you can trap a whole lot of charged particles, positrons or antiprotons. My experiment is orders of magnitude more difficult because when I take an antiproton and give it a positron, I end up with 0 net charge, so it's neutral. However, it's slightly magnetic. You can think of it as kind of a microscopic compass needle. So I can use incredibly strong magnetic fields to hold it, all right? That's much, much, much more difficult than holding the charged particles. Alpha is the only experiment in the world that's ever done that. We do it now routinely, but it took 30 years really to get to where we can do this comfortably.
So there are 2 more questions I want to cover before we finish.
Sure.
One of them we did cover already, but I think it's a really nice way to end. So the one question I saw that was pinned is, what is the ultimate aim of this research? What is the goal?
Okay, we're trying to understand the fundamental rules about how the universe is screwed together. We want to know if matter and antimatter really are equal but opposites. And we want to learn that by doing very high precision experiments, right? Very, very carefully controlled precision experiments based on atomic physics, not high energy physics. That's what we're doing in this building. We're using the techniques of atomic physics to see if there's maybe some really small difference between matter and antimatter that's been overlooked in our theory. Some new physics. It's always about new physics, things we really haven't anticipated yet or haven't observed. So it's basic knowledge at its most basic. You can, I often say, this is question 0. Why is the universe still here? Right? Why did it evolve in matter and not antimatter, or not just annihilate itself? So it's sort of the most basic things you can ask.
Yeah, it's really, so it's about the curiosity. We don't really have time to talk about it in this slide, but there's a lot of technology that also comes from this kind of research. And antimatter, I think, is also a really important one because there's a lot of medical technology that comes from better understanding antimatter. I mean, there's antimatter in PET scanners,
That's right.
positron emission tomography scanners, and the magnets that we use in our facilities are also used in things like MRI
Sure.
machines.
Most of medical imaging was started by some physicists for some completely other reason. Right.
So it's not something that we do day to day, but it is a really nice sort of, I'm just
And
keeping
as
an
you
eye on the
probably
time.
know, the World Wide Web was invented here. Not our fault, right? We had nothing to do with that, but that was a byproduct of scientists wanting to share information.
Great, and I think we've got 1 minute left before the live finishes. So
Okay.
the last question, which we touched on a little bit, but is your job fun?
I have the best job in the world. In fact, I wouldn't know what else to do. I have a unique experiment, a unique group of people. We're doing something that only we can do. Everything that we learn is the first time anyone has seen it. I mean, what could be better than that? It's just amazing.
Perfect. So I think that's the best way to end this live. So thank you so much for joining. We've been here in the Antimatter Factory here at CERN, and this has been part of TikTok UK's Summer Skills program. It's still going on for a number of weeks. This week was STEM week, and next week you get a new topic, so go and check that out. And thanks so much for joining me.
Thanks for listening. Great questions.
Yeah, thanks
Tune
so
in
much.
to Clara another time.
Thanks. Yeah, if you want to learn more about physics at CERN, do follow this account, and we also have a CERN account too that you can go and follow as well. So thanks for joining, and we will see you again in another live.
Bye-bye.
Bye.